Hi, everyone. My name is Kesav Viswanadha,
And my name is Indaheng.
and we're happy to present our work using Scenic and VerifAI for parallel and multi-objective falsification of AI-based systems. Consider, for example, the domain of autonomous driving. Self-driving has remarkable promise for eventually reducing the number of road accidents and increasing traffic mobility. However, as this developing technology is making its way onto the road, bugs and unaccounted edge cases can lead to devastating accidents and loss of life. This makes reliable and effective testing methods a crucial aspect to move towards safe autonomy. Unlike more traditional software systems, AVs have some specific challenges to testing. First off, neural network components contain possibly millions of parameters, making it impractically complex to reason about them. Furthermore, there are an infinite number of possible scenarios that an AV might encounter, which makes it difficult to ever confidently assert that a system is sufficiently well tested. Finally, there's a long tail of rare edge cases that can individually occur infrequently, but in aggregate, they pose a significant risk. For instance, a recent Twitter post in June described a Tesla autopilot system that was struggling to comprehend a truck carrying traffic lights, as shown in the image on the right.
So first, to give some background on Scenic, it is a probabilistic programming language embedded in Python, whose syntax and semantics are designed to model abstract scenarios involving dynamic and interactive agent behaviors. An abstract scenario encoded as a Scenic program represents a distribution over the initial states and the behaviors of agents in the scenario. Meanwhile, a concrete scenario is a sampled scenario from these distributions with concrete values assigned to the initial states and behaviors rather than the distributions. In this example, a Scenic program is shown that models a badly parked car on a side of the road, abruptly pulling into a lane where the ego vehicle is driving. In lines 12 through 22, we model a distribution over the initial states of the ego and the badly parked vehicle. For instance, in line 15, a distribution is assigned to the bad angle with which the car is parked. Then in lines 1 through 10, dynamic agent behaviors are modeled. In line 6, the ego behavior will execute the follow lane behavior by default, as stated in line 8. But when any object is within some safety distance from the ego, it will execute a collision avoidance maneuver, as stated in line 10. Thus, we can think of a Scenic program as succinctly representing an abstract scenario from which we can sample a distribution of concrete scenarios. A Scenic program can not only model, but also generate dynamic and interactive scenarios and simulations. As to this generation process, please refer to the cited Scenic paper.
Our work extends the existing VerifAI toolkit. Here we explain the existing VerifAI and then describe how we built upon it. So VerifAI is a toolkit for formal design and analysis of systems that include artificial intelligence and machine learning components. It takes in 3 inputs: a system of interest, such as an autonomous driving system, an environment model, and a property or evaluation metric. There are various use cases for VerifAI as shown on the right. VerifAI supports environment modeling in Scenic. That means that given a Scenic program, VerifAI Toolkit automatically extracts an abstract feature space consisting of the semantic features, such as the agent's position, heading angle, and behaviors, and the distributions over them as defined in the program. To analyze how a system performs in a given abstract scenario, we need to efficiently explore this abstract feature space via sampling. A sample from this feature space corresponds to a concrete scenario. VerifAI supports various sampling algorithms for this process. In each sampled scenario, an input system's performance is evaluated by the monitor in VerifAI using the inputted property or evaluation metric. The sampled environment's concrete semantic feature values and corresponding system performance are then logged for further analysis. Also, the performance of the system evaluated in the monitor is provided to the sampling algorithms to more intelligently sample the next environment. We extended VerifAI in 3 major aspects. First, we support parallelization of simulations to expedite the analysis process. Second, we support multi-objective property specification. And the third is a sampling technique for these multi-objective properties. In The next slide, we will show the existing VerifAI architecture, and then we will show our extension with parallelization. The architecture of the existing VerifAI is shown in this diagram, and the updated parallelized architecture will be shown next. So the existing VerifAI instantiates what is called the Scenic server, and this is actually an artifact of VerifAI. And what it does is it acts like a manager that coordinates the communication between Scenic and the simulator. From there, this back and forth communication continues until either a termination condition is met or the simulation times out. Then the trajectories of all these agents are sent to the monitor, which generates what's called a satisfaction value. And this basically tells us by how much we either violated or satisfied each of our constraints in the specification. And this information gets sent back to the falsifier, which saves all of this in an error table for future analysis. This is the architecture of our extended VerifAI toolkit, which supports parallelization of simulations. We instantiate multiple instances of our simulator and start up multiple parallel workers from within the Scenic server, which communicate with these separate instances of the simulator. These results are centrally managed by the Scenic server, and anytime a simulation finishes, it is sent to the monitor to update the falsification process asynchronously. Now we describe our second contribution to VerifAI. The existing VerifAI toolkit only allowed specifying a single evaluation metric. However, in practice, there is a need for specifying multiple evaluation metrics for testing autonomous vehicles, and different priorities may be assigned to these metrics. For example, an autonomous vehicle should reach its given destination without colliding with any object. It should also obey traffic laws and maintain a safe distance from other vehicles, but these are obviously less important than not crashing. We use the concept of rulebooks to encode a partial ordering of these various evaluation metrics. A rulebook is a directed graph where the nodes are the various objectives, and a directed edge from one node to another represents their relative priorities. For example, in the rulebook on the right, row 1 could be the no collisions objective, row 2 could be obey traffic laws, and row 3 could be maintain minimum safe distance. From this rulebook, we can make several inferences, such as row 1 is more important than row 2, and row 1 is more important than row 3. But row 2 and row 3 are incomparable as one is not directly downstream of the other. Our third contribution is developing a sampler to support the multi-objective evaluation metric. We developed the multi-arm Bandit sampler, which balances a trade-off between exploitation, or actively searching for counterexamples like our cross-entropy sampler does, and exploration, or sampling a diverse set of test cases evenly across the feature space like our Halton sampler does. The equation on the right says that the next sample to generate is dependent on the average number of counterexamples we've seen in a given region of the search space, which is given by the mu I hat of t-1 value. And it's also dependent on the number of times that we have previously sampled from that region, which is this value t sub I of t-1. This sampling strategy is especially important when optimizing for multiple objectives, as we don't want the active search process to be heavily biased by the results of the initial few samples, as often happens with the cross-entropy sampler. We now present our incremental algorithm for finding violations of the metrics that we specify. When dealing with the multidimensional objective, the value mu I hat of t-1 is not so easy to compute, as it's not immediately obvious what constitutes a counterexample. For this approach, we chose to always optimize for the current maximal counterexample found. So that means if we find any sample that has a satisfaction value at least as bad as the worst sample we have found so far, and this is of course determined partially by our rulebook as well, or if the satisfaction values of these two samples are incomparable, then we consider this a counterexample. There are of course many other ideas that could have been tried, but this one seems to work well in practice, as we will discuss later on in the experiments section.
For our experiments, we put together a library of scenic programs. These scenarios were derived from a publication by the National Highway Traffic Safety Administration that covers common driving situations that often lead to crashes for human drivers. We grouped the scenarios into 4 broad classes that were intersection, bypassing, merging, and pedestrians. And note that these cover various aspects such as road structures, agent behaviors, and the type of agents in the scenarios. These scenic programs were executed in the Carla Autonomous Driving Simulator, and we ran each scenario for 30 minutes with a variety of the different samplers, both with and without parallelism.
Here are the results of running the parallelized pipeline for falsification. For all of the experiments with parallelism turned on, 5 parallel workers were used as we did not have the computational resources to go beyond that. The orange bars show the percentage of counterexamples found for various scenarios and configurations of the experiment. We can see visually that the parallelized experiments generated many more samples in the same amount of time as compared to our previous architecture. We also quantify this benchmark more concretely by looking at 2 metrics. First is the speed up factor, which looks at just the ratio of the number of samples generated for parallel and serial falsification. Those values are given here in the first row of this table, and we can see that we get about roughly a 3 to 5x speed up on average. We also generate a confidence interval, which estimates the proportion of generated samples that are counterexamples. Since this process assumes random sampling, we compute these confidence intervals only for experiments involving the Halton sampler, which is an approximation for uniform random sampling. We can see that the intervals are roughly half as wide for the parallelized experiments, which means we are getting a tighter bound on the true value that we are trying to estimate. And this makes sense because the width of this confidence interval is inversely proportional to the square root of the number of samples that we generate. So this is around approximately what the values we expect to see are. We also use these experiments to look at how the generated samples are distributed across the feature space defined by a scenic program. For one of our scenarios, we had 3 parameters: the speed of the ego vehicle, the distance of the ego vehicle from an intersection, and for a pedestrian crossing through the intersection, we sampled the amount of time that they wait in the middle of the intersection before continuing to cross. We plotted the sampled values for each of these 3 parameters for 3 different samplers, and it is visually obvious that the multi-armed Bandit sampling is a middle ground between cross-entropy sampling as shown on the left, which is a pure active search, and Halton sampling on the right, which is purely randomized sampling. We also ran an experiment to test our approach to multi-objective falsification. We developed a scenic program which specifies 5 adversary vehicles approaching an intersection in addition to the ego vehicle. The multi-objective specification we used is that the ego must stay at least 5 meters away from each of the other 5 vehicles at all times. We tried a variety of rulebook orderings for this, including the one shown on the right. Using parallelized multi-objective falsification for 30 minutes, we were able to falsify all 5 objectives for many orderings and at least 4 out of 5 for all of the others. When we instead tried to write this specification as a union or intersection using and or to combine all of these objectives into one, the cross-entropy sampler failed to find any counterexamples when run for 30 minutes or even up to 1 hour. So in summary, our enhancements to VerifAI and Scenic have greatly improved the efficiency as well as the complexity of specifications that can be falsified. For these benefits to be fully realized for production systems, 2 aspects need to be addressed. First, there needs to be more research into scaling up this system to take advantage of cloud instances so that hundreds or even thousands of parallel workers can be used at the same time. Additionally, as with all simulation-based methods, it would benefit from more research to bridge the real-world to simulation gap. And we hope that this work can be used to effectively guide the types of tests performed in the real world to save time and resources. In conclusion, we think this approach to testing of AI-based systems has great promise for future development. Thank you very much.